last class we have studied about n channel enhancement type MOSFET. We have seen the VI characteristic of this n channel enhancement type MOSFET. Now, the transfer characteristic for the n channel enhancement type MOSFET will be studied. Now, how to draw the transfer characteristic, that we will see now. First of all, what is the transfer characteristic? What does the transfer characteristic mean? So, the transfer characteristic, it is the relation between the input and output. So, for this n channel enhancement type MOSFET, the input is the voltage between gate and source, and the output is the drain to source current. So, if we vary the gate to source voltage, then the drain current, then drain to source current will vary. So, the controlling quantity is the gate to source voltage. So, now from the transfer characteristic we can know about the behavior of the device. So, let us now try to draw the transfer characteristic for this n channel enhancement type MOSFET. We know about the VI characteristic, that is the characteristic between the drain current and the drain to source voltage for various values of gate to source voltage. So, we basically have seen in the last class how for various values of the gate to source voltage we get the plots between the drain current and the gate drain to source voltage. Now, from this VI characteristic or drain characteristic, we can draw the transfer characteristic. So, let us see here, we are now showing here the drain characteristic for an n channel enhancement type MOSFET, and by the side of this drain characteristic is shown the transfer characteristic. Now, how have we got this transfer characteristic? We have in the drain characteristic or the VI characteristic the plot between the drain current and the drain to source voltage for various values of the gate to source voltage. Now, we know for a particular n channel MOSFET device the threshold voltage. So, for example, let us consider for this particular device what we are considering right now is having a threshold voltage of plus 2 volt. That is, if the gate to source voltage is below that threshold voltage, then the current from drain to source will be 0, that we discussed in the last class. So, for gate to source voltage below 2 volt, the current is 0, drain to source current is 0. Now, we are increasing the gate to source voltage beyond 2 volt, and we have these different plots, each plot for a particular gate to source voltage. For example, we are varying the gate to source voltage from 3 volt to 8 volt, say. For 3 volt is a small drain to source current will flow and which will be saturated after some voltage between drain to source. So, that voltage of saturation between drain to source, that also we know, that is equal to gate to source voltage minus threshold voltage. If we are giving gate to source voltage 3 volt, 3 minus 2, 1 volt is the saturation voltage between drain to source, at which the saturation current in the drain will flow. Similarly, for different values of the gate to source voltage, we have these plots, and by the side of it, if we want to draw the transfer characteristic, then we must plot the points for a particular gate to source voltage, what will be the saturation drain current. So, that will be giving a point. So, joining all these corresponding points, we will get a curve, we will be getting a nonlinear curve, that will be the transfer characteristic. That is the characteristic between the drain current and the gate to source voltage. So, here in this plot we are drawing the transfer characteristic by extending the saturated current and finding out the intersecting point between these values of the saturating current with the corresponding gate to source voltage. So, the V and I axis will be here gate to source voltage and the drain current, VGS in volt and the drain current in milliampere. And we are plotting the VI characteristic or the drain characteristic for gate to source voltage from 3 volt onwards, 3, 4, 5, 6, 7, 8 volts. So, in the V axis, that is VGS or gate to source volt will be 1, 2, 3 etc. up to 8 we are marking in the VGS axis, this is volt, and in the ID axis or ID milliampere, it is in the order of, in the y axis, this is the current axis, we are having the corresponding order of the drain current, which is 1 to up to 10 say. So, this voltage and current axis are plotted and marked accordingly. Now, for example, VGS is equal to 3 volt, this is the current, saturation current. So, we extend it and this current is crossing or intersecting the VGS 3 volt at this point. So, this is one point. Obviously, the earlier point is 0 current and 2 volt, because for VGS 2 volt, which is the threshold voltage, the current, drain current is 0. So, 2 volt and 0 milliampere drain current, this is one point actually. It will be starting from this point and it will be continuing. That plot can be obtained by joining all the points whose coordinates are VGS and ID. So, in this drain characteristic, the saturation current is just extended and the intersecting point between this saturating current and the corresponding gate to source voltage is that point which we have to obtain. So, for VGS is equal to 4 volts say, we are extending this drain current, which is the saturation current, beyond this axis and it is extended, it is meeting the 4 voltage gate to source at this point. Similarly, for 5 voltage VGS, this is the point, the saturation drain current is meeting the corresponding gate to source voltage 5 volt at this point. So, correspondingly these are the points which can be obtained accordingly, and by joining these points we get the transfer characteristic. So, this transfer characteristic is the characteristic which we have obtained from the VI characteristic. Now, this n channel enhancement type MOSFET we have discussed, and we have already seen how the VI characteristic and the transfer characteristic are obtained. Now, there is another type of MOSFET which we are going to study now. This is the depletion type of MOSFET. Now, before going to the depletion type of MOSFET, in order to complete the enhancement type MOSFET, we will be considering the P channel enhancement type MOSFET, because till now we have discussed about the N channel enhancement type MOSFET. It is enhancement type MOSFET, but we are considering the N channel type. Now, what will be the physical structure like for the P channel enhancement type MOSFET? If we now consider the physical structure of the P channel enhancement type MOSFET, then we will be having two P type semiconductors and the substrate will be of N type. Now, the gate to source voltage will be having polarity as shown here. It will be negative, the gate potential will be negative with respect to the source, and we will be applying the drain to source voltage as shown with such polarity that the drain is negative with respect to the source. So, now what will happen, as we are having a negative potential at the gate with respect to the source, so the minority carriers of the N substrate which are holes, they will be attracted by the gate to source voltage negative terminal, and the majority carriers of the N type substrate which are electrons, they will be repelled by the negative terminal of the gate to source voltage. So, we will be having a channel of holes between these two P types. So, this will be a channel which will be having the charge carriers which are positive, and when the number of positive charge carriers are enough to sustain the current, the drain current will flow, but the direction of the drain current will be as shown here, and which is equal to the source current. So, this is just reverse of what we got in the N channel enhancement type MOSFET. So, the P channel enhancement type MOSFET will be having the characteristic or VI characteristic. If we plot, the curves will be similar to those we have obtained in the earlier case of the N channel MOSFET, but VGS is negative, say minus 3 volt, minus 4 volt, etc. Of course, these are the horizontal, not this will be horizontal curves like this. As saturation is happening, so if we have this plot of ID versus VDS for a particular gate to source voltage, then we will be getting saturation when VDS equal to VGS minus V threshold. So, here actually the polarities of the potentials are different than those earlier N channel case, and the current directions will also be accordingly. So, from this plot we can also draw the transfer characteristic for the P channel enhancement type MOSFET. So, now typically the values of the silicon dioxide insulating materials thickness, if we consider that, it will be around 0.02 micrometer to 0.1 micrometer. That means, the silicon dioxide material, which is the insulating material, it is having a thin layer of around 0.02 micrometer to 0.1 micrometer thickness, and typical length of the channel L is from 1 micrometer to 10 micrometer, and the channel width, which is W, it is between 2 micrometer to 500 micrometer. So, these are some typical values or parameters for this MOSFET. Now, if we consider the N channel enhancement type MOSFET and draw the symbol for that N channel enhancement type MOSFET, for a 4 terminal and N channel enhancement type MOSFET, this is the symbol having the 4 terminals. So, here the symbol itself is explicitly reflecting some of the information, like when we have the symbol for this N channel enhancement type MOSFET, this is the symbol. Here we see that there is a gap between the gate and the body. Basically, this gap signifies the insulating material silicon dioxide, which separates the gate from the body of the MOSFET, and these 3 broken lines are signifying the absence of a channel between the drain and the source. Between drain and source, exactly as we have seen, there is no channel established. Only after we apply the gate to source voltage, then only we can establish a channel. So, that is significantly reflected by these broken lines, and this is the substrate terminal. This arrow mark is signifying the direction of current between P and N, because it is an N channel. In N channel, P is the substrate. So, the current is from P to N, that is the normal direction of current in a PN, that is significantly reflected by this symbol, and this symbol is for external connection of the substrate terminal. If we have internal connection of the substrate terminal between the substrate and the source, then we have this symbol, because here we are showing that the substrate and source are connected. So, this is a 3 terminal, but here it is a 4 terminal. So, this case is 4 terminal and this case is 3 terminal. So, this is the symbol for the N channel enhancement type MOSFET. Now, the symbol for P channel enhancement type MOSFET, others being same, only the direction of the arrow, because it is a P channel means the substrate is N. So, the current direction is from P to N, and this is the 4 terminal, this is the 3 terminal symbol. Now, we will discuss about another type of MOSFET, which is the depletion type MOSFET. We have discussed about the enhancement type MOSFET. Now, we will be discussing about the depletion type MOSFET, and let us first discuss N channel depletion type MOSFET. So, there are N channel as well as p channel depletion type MOSFET, but we will be discussing about the n channel first, n channel depletion type MOSFET. So, here the physical structure for the n channel depletion type MOSFET is shown here. Now, the substrate is P, there are drain and source made of n type materials, but one difference from the enhancement type MOSFET is that there is an n type material as a channel between drain and source, which is already existing. In enhancement type MOSFET, we did not have a channel, or we did not have a n type or p type material in between the drain and source. The reason between drain and source was not having any channel, but here an n type material is existing between the drain and the source. So, we have already an n channel. Others being same, means we have the drain terminal, gate terminal and source terminal taken out from the metal contacts, which are grown over the silicon dioxide, and the substrate terminal. So, this is the 4 terminal case. So, the physical structure of a depletion type MOSFET is as shown in this figure. Now, let us see how the current conduction takes place. For that, let us first consider that gate to source voltage is 0. Now, as this is a MOSFET having p type substrate, n type drain and source, and there is an n channel in between drain and source. So, the p type substrate is having holes as the majority carriers and electrons as the minority carriers. Now, let us apply a positive voltage between the drain and the source. VDS is positive. So, if VDS is positive and we are not having any gate to source voltage, but because there are abundance of electrons in the n channel, there are already free charge carriers, electrons available in the n channel. So, these electrons will be attracted by the positive terminal of the drain to source voltage. So, there will be flow of electrons through the n channel between the two n type materials. So, the conventional current flow will be as shown in this arrow mark, and that current is, say, the drain current is flowing and it will be entering into that negative of the terminal of VDS. So, drain current and source current both are equal. When VGS is equal to 0, that current which flows between drain and source is named as IDSS, and this is a specific current value which is specified in the MOSFET. That is, for a device we know the value of the IDSS from the data sheet. It is specified that this is the value of the IDSS. So, that means even when the gate to source voltage is 0, there is a flow of the current between drain and source, that current is IDSS. Now, what will happen when we have, say, gate to source voltage negative, drain to source voltage is positive, but gate to source voltage let us make negative. We are applying a negative voltage between gate and source. Now, what will happen as the gate to source voltage is negative, the electrons in the n channel, they will be repelled or pushed by the negative terminal of the gate to source voltage, and the holes which are the majority carriers in the p substrate, those will be attracted by the negative terminal of the gate to source voltage. So, in the process, these electrons and these holes, when they travel towards each other because of the impact of this gate to source negative voltage, there will be some recombination taking place in between the electrons and the holes. So, because of that, the current ID will be now decreasing, because some electrons are lost because of recombination with the holes coming from the p substrate. So, total number of free electrons which took part in the conduction of the current will be now reduced. That is why the ID current will be now decreasing. Now, if we go on decreasing the VGS further, we go on decreasing the gate to source voltage even further, then the drain to source current will be going on decreasing and decreasing, and ultimately a point will be reached when it will be 0, because as the number of free electrons are going on reducing because of the recombination taking place, and as we go on increasing the gate to source negative voltage, there will be more and more recombination taking place. Ultimately, this whole channel will be depleted of any single electron. That means, there will be no single electron existing in the channel to take part in the conduction of current. The channel will be totally depleted of the free charge carriers electrons. So, the current will be diminishing to 0. That particular gate to source voltage at which the drain to source current becomes 0, because there is complete depletion of the electrons in the channel, that voltage is called the threshold voltage. And here the threshold voltage is negative, that has to be kept in mind, because we are applying a negative gate to source voltage, and the threshold voltage is that voltage, that negative voltage between gate to source, when the current from drain to source will be 0. So, this is the reason why this type of MOSFET is known as depletion type MOSFET. The name originates from this depletion, but then there is another phenomenon also, which is the enhancement phenomenon. That will be clear if we now see the situation when gate to source voltage is positive. Now, when we apply gate to source voltage positive, what will happen is that this positive terminal of the gate to source voltage will be attracting the minority carriers, which are electrons, from the p substrate. Because we have the p substrate, p type material, and p type material has majority carriers as holes and minority carriers as electrons. So, apart from the electrons which are being already present in the n channel, when we apply the gate to source voltage positive, then the positive terminal of the gate to source voltage will attract minority carriers electrons from the p substrate, and that is why we are now having extra electrons than what were present in the n channel originally. So, now because of the increment in the free charge carriers which are electrons, there will be increment in the drain to source current. Now, if we go on increasing this VGS further, the current between drain to source will be going on increasing. Now, as this VGS is increased, then the kinetic energy which is achieved by the electrons, that will be increasing. So, they will be knocking out more free electrons from the covalent bonds, and this process will be accumulating. So, we have much more electrons being given part-2 by this process. So, basically what we have, when we have a VGS positive, then we have abundance of electrons which are due to the fact that the positive terminal of VGS is now attracting minority carriers from the p substrate, and these minority carriers take part in knocking out more electrons because their kinetic energy is now increased because of the application of the gate to source positive voltage. So, basically what we have is that we have a greater drain to source current. So, there is enhancement in the current flow. So, there is enhancement also, there was depletion phenomenon also which was taking place when VGS was negative. So, what we notice in this type of MOSFET is that both the phenomena of depletion and the enhancement take place, and this can be represented by the regions from gate to source voltage 0 to the left and right. If we have gate to source voltage 0, then what we have is that on the one side if we have suppose gate to source VGS 0, here to the right it is positive, to the left it is negative, then what has been observed is that there are two phenomena, depletion and enhancement. When gate to source voltage was negative, we had the phenomenon of depletion. So, the depletion phenomenon occurs when the gate to source voltage is negative, and the enhancement phenomenon occurs when the gate to source voltage is positive, and the current which flows when VGS is equal to 0 is IDSS. That is a specific current which has its value given in the data sheet for a particular MOSFET device, which is of course the depletion type MOSFET. So, although the name of the MOSFET is depletion type, but actually both the depletion and enhancement phenomena are occurring depending upon the gate to source voltage, whether it is negative or positive. Now, if we now see the VI characteristic, after knowing all this about the different regions of operation, knowing about depletion and enhancement, that is whether VGS is 0 or negative or positive, we can now plot very easily the VI characteristic. So, for the depletion type MOSFET, the VI characteristic if we draw, putting as usual in the x axis the drain to source voltage, and in the y axis the current ID in the order of milliampere, of course it is, and for different values of the gate to source voltage. So, when VGS is equal to 0, say this is when VGS is equal to 0, the current which flows between drain to source is known as IDSS. It has a value given in the data sheet. Now, we have seen that the threshold voltage which is negative for this n channel depletion type MOSFET is that value of the gate to source voltage at which the drain to source current becomes 0. And let us, for this particular device for which we are plotting the Vi characteristic, have a threshold voltage minus 4 volt. So, just this is an example we are taking to draw the Vi characteristic. So, when Vt is minus 4 volt, threshold voltage is minus 4 volt, then if gate to source voltage is below minus 4 volt, the magnitude of the gate to source voltage is below minus 4 volt, then it will be the current between drain to source is equal to 0. So, this is the cutoff, this is the cutoff region. Cutoff means no current, 0 current. Now, when we have gate to source voltage greater than threshold voltage, of course, it is still negative, but it is greater than the threshold voltage minus 4 volt. Suppose it is minus 3 volt, then current will be flowing and it will be reaching the saturation value at a voltage which is defined by Vgs minus Vt. So, if the drain to source voltage is equal to Vgs minus Vt, now mind it that for this particular characteristic or for this particular device under study, we have threshold voltage is negative. So, if Vgs is equal to minus 3 volt, we are taking minus 3 minus Vt again minus 4. So, minus 3 plus 4 means 1 volt. So, that means that the current between drain to source will become saturated. It will be not increasing beyond this value at a voltage equal to 1 volt. So, that means here actually this is around 1 volt, we get the saturation between the drain to source current. Similarly, if we go on increasing the gate to source voltage, if now gate to source voltage is minus 2 volt, then the saturation value of the drain to source voltage will be minus 2 minus threshold, minus 2 minus 4, that means minus 2 plus 4, that is 2 volt. So, around 2 volt we will be having the saturation occurring, that means after this value, even if you go on increasing the drain to source voltage, the current between drain to source is not going to increase, it will become saturated. So, similarly we can carry on. When Vgs is equal to 0, we know that we have got this IDSS, that is the drain to source current. Now, this region between cutoff and the drain to source saturation current, that is drain to source saturation current when Vgs is equal to 0. So, from this point to this point, actually this is your depletion phenomenon is going on. So, this is the depletion region. Now, if we go on increasing the gate to source voltage in the positive direction, suppose Vgs is equal to 1 volt. So, now enhancement phenomenon will be happening, current will be increasing and drain to source current will be very much increased, and that fact is reflected in this gap. If we look into the gap between Vgs 0 volt and Vgs plus 1 volt and the gap between Vgs 0 volt and Vgs minus 1 volt, this gap in the positive direction is much higher. That signifies that the drain to source current is now much higher. So, drain to source current is increasing, and this will be continuing if we go on increasing this gate to source voltage in a positive direction, say 2 volt. So, the drain to source current will be increasing and increasing. So, this region actually, in this region enhancement phenomena is occurring, and the saturation voltage between drain and source VDS, which is equal to VGS minus VT. So, when VGS is equal to positive, say for example 1 volt, 1 minus 4 volt will be VDS, which is equal to 5 volt, positive 5 volt, and so the curves will be bending towards right, because the locus of this drain to source saturation voltage is given by this dotted line, dotted curve. This equation for this dotted curve is VDS is equal to VGS minus VT. That is the value of the drain to source saturation voltage. And to the right, saturation is happening where VDS is greater than equal to VGS minus VT. Actually, in fact, it is greater than, equal to is this point, and to the left VDS is less than VGS minus VT, which region is known as triode region, and this region is known as saturation region, and actually this is cutoff region. This region is cutoff region when current is 0, and that is when VGS is equal to minus VGS is equal to threshold voltage VT. So, this plot is explaining the phenomenons of depletion and enhancement occurring in the depletion type MOSFET. So, now we understand that although the name is depletion type, basically it is having both the phenomenon of depletion and enhancement. And from this drain characteristic or VI characteristic, we can project it for obtaining the transfer characteristic. If we want to plot the transfer characteristic, that is the characteristic between the drain current and the VGS, what we do is that for each of these plots, we just extend or project the saturation currents and let it meet with the corresponding VGS. So, for example, here VGS is equal to minus 3 volt, we extend it to the left. When minus 3 volt, in the x axis or voltage axis, we see that this is 0, VGS is equal to 0. To the right, this axis having positive VGS, to the left this axis is having negative VGS. Threshold voltage is minus 4 volt for this example, this is the point. Now, to the left, when the depletion phenomenon is occurring or in the depletion mode of operation, the MOSFET is in the depletion mode of operation. So, the current when it meets that minus 3 volt, this point, the point we just mark this point, and next is minus 2 volt VGS. At this voltage, the current, saturation current, the current is extended to the left and it is meeting the VGS minus 2 volt at this point. Similarly, all these points, if we now connect, we get a curve, and that is a transfer characteristic. Here VGS is equal to 0. So, to the left, the MOSFET is under depletion mode of operation, and to the right of 0, when VGS is equal to positive, this is under enhancement mode of operation. So, from these figures, we now have a clear idea how the transfer characteristic can be obtained, and that is shown on the side of this BI characteristic or the drain characteristic for easy understanding. Now, the symbol for the N channel depletion type MOSFET is shown here, which is showing the gate having a gap with the body of the device, signifying the insulating material. So, this gap will be signifying the insulating material, as was present in the earlier example that we saw in enhancement type MOSFET. Now, one significant difference between the enhancement and depletion type MOSFET as far as symbol is concerned is here that we have an unbroken line, signifying that there is a channel present between drain and source. If you recall earlier, when we are considering enhancement type MOSFET, there was broken line, that is in between drain and source we did not have a channel, that is signifying the absence of a channel means the symbol also is reflecting that by showing broken lines. But here there is a channel ever present between the drain and source, which is reflected by this continuous unbroken line, that is there is a channel between drain and source. These are the three terminals, drain, gate and source. The substrate terminal is this one, and it has the direction of the arrow signifying whether the substrate is p type or p or n, and we are considering an n channel substrate and n channel MOSFET. The substrate is p. So, as the substrate is p, the current direction from p to n, that is why it is in this way. Now, this symbol is for substrate being external, having external connection, that is we have 4 terminals, one terminal for the substrate is also available, but what is more common is that to show the substrate connected to the source. So, in this symbol we have seen that the source and the substrate are connected, all others are same, all other parts of the symbol are same, only the difference is that the substrate is connected to the source internally. So, this is internal symbol, internal connection of substrate, this is external connection of substrate, and this is n channel, which is represented by the direction of the arrow. We have a p substrate, so the current will be from p to n normally. So, that is p to n direction of current is shown by this arrow. Now, if we have a p channel depletion type MOSFET, in p channel depletion type MOSFET, the substrate will be having n type materials and the channel is p. So, others remaining same, the arrowhead of the substrate, in the substrate connection or the arrowhead will be just opposite to the n channel, it will be from left to right, because we have in the p channel p channel depletion type MOSFET. We have channel made of p, that is the substrate will be made of n type material, and there will be, of course, this will be there, the silica etc. will be there, silicon dioxide, and this will be p to p, it is p channel, this channel will be p like this. So, these are the drain, source and gate terminal. So, we have this connection between metallic contact and the p is there, the drain is there. Similarly, here also between the metal and the source there will be a contact, metallic contact. So, now this is the drain and this is the source. So, here channel is made of p. So, now if we look into the direction of current between the substrate and this p type, it will be in this direction. That is why we have the direction of the arrow from left to right as is shown here. And this is 4 terminal case where you have the substrate terminal also available, but internal connection when you consider, there will be the connection between the substrate and the source. So, we have 3 terminals only. Now, the transfer characteristic, if we consider for the p channel type of MOSFET, it will be just a mirror image for the n channel, but that will be bending towards left, like it will be having, say this is 0, I am considering for p channel. So, if it is 0, then it will be -1, -2, like it will be negative, here it will be positive. So, the transfer characteristic will be bending towards left. That is just if you flip the n channel type transfer characteristic, that means it will be something like this. So, earlier we have got this type when we are considering n channel. Now, this is for p channel, the solid line is for p channel. So, this gives you the IDSS. So, the transfer characteristic for a p channel type MOSFET, even for this enhancement type or depletion type, if we consider, they will be just flipped version to the left, or it will be just bending towards left of that what was obtained for the n channel type. So, now we know about the different structures of the MOSFET device. In our lectures, we have discussed about basically 2 different variations of MOSFET. One is the enhancement type MOSFET and the other is the depletion type MOSFET. We have discussed about n channel and p channel type of MOSFET, both for enhancement as well as depletion types. We have seen how the current conduction takes place between drain and source, and how if we vary the gate to source voltage, the drain to source current changes, how saturation is obtained depending upon the value of the drain to source voltage. We get saturation, means the current between drain to source does not vary beyond a point when saturation is reached, and from the saturation current and corresponding gate to source voltage, we have found out the transfer characteristic. So, all these studies help us in understanding the final use where we are going to apply the MOSFET device, that is for amplifier. So, in the next classes, with the background of what we have studied till now, with this understanding, we will be proceeding to study the amplifier using the MOSFET device. And for amplifier, we know that we have to know the DC biasing also. So, we will be discussing about the DC biasing methods, and then we will be proceeding to find out basically the different parameters related to amplifier where the MOSFET device is used.